Hello, everyone. This is lecture 2 of Petroleum Reservoir Geomechanics. Last time we went through some logistics. There is a small change in a sense of the class went from 2 days a week, 75-minute lectures, to 3 times a week, 50-minute lectures. So there is a little bit of restructuring going on, but other than that, we should be okay. I went through the main logistics in regard to to what the class would be about. We talked about the content a little bit, the structure, the TA, the prerequisites, how this class is connected to other classes that you are going to take before and after. That you will take after or you took before. Then we talk about things that you should avoid in order to get increase your chances to make a very good grade at the end of the year. I think all of you should have a chance to make a good grade at the end of the year. I think I had one mistake in the syllabus. I had 2023 for the final, and I fixed that. The final is going to be December 16, 2024, 3:15 to 5:15. So it's 2 hours. And I have no control on that in regard to they arrange the dates based on when the lecture is. For the exams, I did file for the dates that I mentioned, and I haven't heard anything negative yet. So unless something crazy comes up, another pandemic or something, October 4th, November 15th, both on a Friday, these would be the exams. It's a little bit intentional that they are a little bit later in the semester. Also, you will notice that the first exam, the first homework won't be given until like a couple weeks and a half, maybe. I don't know about this class. When is the first homework due? But well, the other class I'm taking, it's a little bit further later on. But this one is, I think it won't be next week, that's for sure. But it's because there are some changes in the roster of the class as we go along. And yeah, I mean, just to make sure that the class roster is settled before we start giving assignments, because if we start grading assignments and new students come in, what am I going to do with those? You know, if the solution key is already out, there is no point. So I want to give some time. Also, given that it's a little bit of a step up, this class, although some of you have already taken 2 classes already from me, it's generally a little bit of a step up. It's a little bit more mathematical. It's more like more intense without wanting to scare anyone. I mean, it's a little bit more involved class. I want to give you some adjustment time. That's why I'm a little bit delaying that. And I think that for the rest of the day today, we will finish module 0. We'll see some general energy stuff. And we'll start with module 1, which is the main technical module, the first technical module of this class that will actually be graded on, I guess, examined on. Maybe later today or most likely on Wednesday, because Monday is a holiday. I will send an announcement on the Blackboard. Monday, I have to shorten my office hours. They are going from 1 to 4 normally. Sorry, Tuesday. But I have a faculty meeting that starts at 3:30. So I will make it something like 3:20. That gives me like 10 minutes to leave my office and go to the faculty meeting. So I will basically cut the office hours shorter for next Tuesday by 40 minutes. But there is still like it's a 2-hour and 20 minutes session. So plenty of time for you to join the Zoom and ask me any questions that you may have, which I don't think there will be by then, because we might have not even started module 1 by then. Anyway, we did stop at, we could talk about things to avoid for not getting a bad grade. Okay, we digested that. Now, I'm gonna have a few slides about the general energy status quo, because most of you, if not all of you, are petroleum engineers or like petroleum engineering students. And you are gonna be working in the field of energy in your careers. Some of you are already working, some of you will get a job. Well, it's the oil and gas industry or the petroleum industry, especially our portion, which is the upstream petroleum industry. It's a big part of the energy business. And energy is a little bit of a buzzword. You hear it a lot in politics, in the TV, in the news, etc., etc. Anyway, so BP, the company BP, every year since 1961, puts together a statistical review of energy. And they basically group together data for consumption, production, per fuel, looks at different fuels, different countries, all put together. And they create a very nice data set that they publish in PDF form and Excel and a spreadsheet form every late June of every year, and that is for the year before. So next June, 2025, it's gonna be published about 2024, about this year, basically. So since then, many companies publish their own data sets. And but because BP has been doing that since 1961, it's been the first one. I mean, Exxon is publishing their own, Chevron, I believe also, certainly the consulting companies like Wood Mackenzie, Deloitte, they do so. But BP has been doing that first, so they have developed some sort of a competitive advantage. Their data sets are more neat, more easy to understand, and easy to interpret, easier to interpret. I have used them many times over the years. There are some discrepancies when you go from one data set to another, and that's because of the way they take into account what we call NGLs, the natural gas liquids. But mostly, but there are some other small errors here and there, but yeah, BP's is pretty good one. So in 2021, I believe, I took the data set and I took the energy consumption for every year, the first year of the first year of the last 5 decades. So 1970, 80, 90, 2000, 2010, 2020. And because 2020 went down as a weird year, I also did 2019. And I divided the consumption into 3 big categories. The purple one is what we call fossil fuels. It's a little bit of a bad name. It's the traditional forms of energy. John D. Rockefeller called them fossil fuels because he thought that would make them sound more valuable. But that's what they tried to make as small as possible. And you see that their consumption has increased by about 150% over 5 decades. From 1970 until 2019, we went from about 200 exajoules, roughly speaking, to 500. That's a 150% increase, I believe. And those are basically coal, oil, natural gas. Then with orange color, we have renewables, which is basically solar, wind, geothermal, this kind of stuff. And those biomass, biofuels, and those are what they try to make as big as possible. And you see they start becoming visible in the 2010, maybe 2000, a little bit, 1%. and they only reached like 6% in the year 2020. That's what they tried to make as big as possible. But of course, you see the percentage-wise on the energy mix, it goes down about 10% from 94 to 84 or 83, but the absolute value is huge. It's massively increasing. And in fact, there was a professor in one university that said that if the market was let alone without any government intervention, this percentage value is going to stabilize somewhere between 87 and 90 and will stay constant throughout the process. So you can argue that the decrease in the purple portion of the total energy mix is almost entirely artificial, as well as the increase in the renewable section. So it seems like from that, the conclusion that we can make is that there are no alternatives to hydrocarbon energy sources in the foreseeable future. And I have this other, in terms of perception, this other plot I made. It shows that the amount of mineral usage in when it comes to wind, offshore, as well as solar, in terms of the mineral usage in terms of rare earth materials and other minerals that are scarce in the earth is much higher for a megawatt of power produced compared to coal and natural gas, which are considered the dirtier types. So you see a little bit of an imbalance here in the perception, but the real imbalance appears here, where I have the energy mix for the 2019, what we saw before in the bars on the 2019 year, 84% fossil fuels, 11% other, and 5% renewables. By the way, other was hydroelectric and nuclear mostly. And on the other side, I have the public spending of the IEA, which is the International Energy Agency, which is a group of 34 countries headquartered in Paris, France. And they are mainly developed nations like the US, first world nations, Britain, France, this kind of countries. And we have here their public spending, the government spending in what is, I put R&D, but they really call it RD&Ds, research, development, and something else, and demonstration. They call it the public funding, government money spent for whatever category, and I divided them into the same categories, and you see only 5% allocated to fossil fuels, 16% to renewables, and 79% on other. Now, other, the yellow part of this right cycle, versus the yellow part of the first cycle on the left, they are different stuff. On the left, we said we had hydroelectric and nuclear. In the right side, we have like transmission efficiency, carbon capture, all this kind of stuff. So it's a little bit of a not applicable comparison when it comes to the yellow portion, but you cannot neglect the imbalance when you see the two sort of pie charts. What else? Let me see. So are we running out of oil? The short answer is no, because the definition of reserves is basically economically extractable oil. So technology and price plays a role on the amount of reserves. I remember, or I read in 2002, the total global oil reserves were about $1 trillion, roughly speaking. It was like 0.97, 0.98 trillion. And in 2012, it was 1.67. So it went up by a lot, by more than 50%. I don't know what is this year, but I would argue that it must be close to 2, if not over. And of course, reserves go down when you produce. But when you are able to extract, every time you discover a new reservoir, a new field, they go up. Every time you invent a new technology, some of you will be working in oil field service companies, research departments, or super major R&D. You are going to be working into trying to find ways to discover more oil. Some of you may be working in independent operators who look for new fields or try to find ways to be profitable in existing fields. And we will be, I think you will understand this much better than the idea that oil is something that was put there at the beginning and this is what it is, and I'm just taking out, because I'm taking oil out of the ground to use it to feed my family, I'm destroying the earth. Now, so if you see that the trends for the solid lines, the dotted lines, which show, they show the reserves, plain reserves. You don't see a dramatic downward trend. Generally, when the reserves go down or go up dramatically for a short period of time is when something is happening that is like energy is like a little bit in the forefront of discussions, like the 2008 economic recession or the 2014 price crash for the oil and gas. You see the oil reserves going down because the price went down. And a lot of fields that were profitable to exploit before are no longer. Now, an interesting thing to note is that there is a little bit of a decoupling between the natural gas and oil that took place from the mid-2000s onwards. That's because of natural gas is emerging as a more practical fluid for this century. It has more legs, as somebody said, than oil. It's cleaner, it's more practical. There are some more, obviously, there is some more challenges associated with its use, but it's slowly becoming more and more the fuel of choice. So it started decoupling also in terms of energy content. If you see the energy content, like 1 BTU in oil is gonna be more expensive than 1 BTU in gas, in terms of gas. I have another graph in another paper of mine that shows, I don't have it here, but it's very similar to the reserves. But if you divide the reserves by the production, you get what we call the R to P ratio, R over P. It roughly says, if you don't discover any new oil or gas from now on, and you keep producing what you are producing right now, how many years you have left. So the value of the units of R over P is in years. And it's on the left axis. And you will see that there is no significant decrease seen from the two solid lines. By the way, the right axis is price per BTU. So you do see the decoupling I mentioned earlier happening by 2005 onwards. I forgot it was normalized by energy content, so it's BTU. Now, carbon tax has been proposed by a lot since, I don't know, the turn of the century, really, and has been thought of as a potential solution. But there is a little bit of a trick associated with carbon tax that makes it a little bit of a very bad idea. That is, the idea in terms of economics is very simple. You have the demand curve going from, if I can write, you have the demand curve going from left top to right bottom. You understand that if something is cheaper, you demand more of it. If something is more expensive, you demand less of it. And then you have the supply going from the bottom left to the top right. And the idea is that you produce more the higher the price it is. And then the idea, idealistically, is that you will get a carbon tax that will shift the supply curve to the left. And now you will get from the old equilibrium, which was, let's just say Q1, quantity 1 to price 1, you're going to move to quantity 2 to price 2. So you are increasing the price and lowering the quantity of what is consumed. And the idea is that you have this green triangle, which is the externality, the cost to third parties, that your own consumption, production of CO2 through consumption of fossil fuels is causing harm to third parties, and you are capturing that using a carbon tax, a carbon taxation scheme. It's a much more complex problem than what I'm making here, but that's the idea here. When you incorporate the societal cost, you are moving the supply curve to the left. And but the tough thing with that is that you need to quantify this damage you are causing to third parties. And it's very hard to do. It's very hard to do it assertively and exactly, yeah.
So basically, it's like when the oil demand is less, so we have less involved third parties.
No, you are not touching the demand. You are moving the supply.
The price is gonna increase if the quantity is less.
The price will increase, yeah. The quantity would be less.
And the third parties are not gonna be involved here.
No, basically you are forcing the market to take account of damage done to the third parties.
Oh, okay, because
yeah, because the market on its own, it won't. That's the idea. And then you have you are shifting the supply curve to the left to create a new price and a new quantity that does account of that triangle.
For example, if the price is gonna go up, so basically people are gonna start drilling more.
Yeah, it's gonna.
Third parties here.
Well, it's gonna be. It's like you are gonna be paying more for gas in the pumps, you know. That's it makes the price higher and the quantity less. But the problem here is that you have to be able to quantify it, and it's not easy. It's not. I don't know if it's possible even, but it does lead to higher prices. And it won't happen in a parliament room or something, or a Congress room, that's for sure. That's the idea, the general idea, yes.
So increasing the price basically is increasing the tax on the suppliers.
Yeah, the price increases because of the tax. It goes from P1 to P2. That's basically it's gonna be the new equilibrium set of prices. And there is also a new equilibrium quantity.
So basically changing in the price. So
it
makes change taxes as well.
Yeah, but it's not by the market. It's like because of the taxation. Now, if I had subsidies, let's say, if I was paying people to burn more fossil fuels, hypothetically, it would have moved, sorry, I pressed the wrong. It would have moved the supply curve to the right. Oops, sorry. Let me go back. I will have moved the supply curve to the right. It's gonna be something like this. It's gonna move like that. And now I will have a new quantity 3. and then a new price that is cheaper. Now I'm making it cheaper because it's a very hypothetical scenario. I'm paying people to burn more oil and gas, right? So I'm doing the opposite. And there is also other stuff that you can do to change the demand as well, but that's a macroeconomical sort of concepts. Yeah, taxes and subsidies impact the supply curves. Incentives and something else impact the demand curves. And there is a reason why the demand curve has this curvature as well. Don't remember what was, but there are reasons for all that. So I took a plot. I took the same data set from BP Statistical Review, and I took them on the vertical axis. I have the CO2 emissions in billion tons of CO2, and then on the horizontal axis, I have the energy consumption per capita in gigajoules per person, basically. And I have the values of the entire world in green turquoise circles with green frame, and the US values with the red squares with a dark blue frame. Now the global values include the US, so that's important that these values are included here. Again, first year of the last 6 decades that we started, basically, or 5 decades, any way you see it. Some people think that the decade starts in like 1971, let's say, not 1970. Yeah. Anyway, but we have 6 values or something, and then for the US and the global. And the vertical axis shows how dirty you are seen as. The horizontal axis shows how wealthy you look on paper. Like energy consumption per capita is considered like, if the energy consumption per capita is high, you are considered a wealthy and developed nation. And on first glance, prima facie, it looks like the US is much more efficient than the world in its entirety. But what is more interesting is this little U-turn that the US appears to be taking around the year 2000. And it goes from small increases in CO2 emissions associated with large leaps in energy consumption per capita. They go to small decreases in CO2 emissions associated with large reductions in energy consumption per capita. And this is concerning. It basically tells you that the goal is changing, has changed somewhere along. Actually, if you make a plot year after year, you are going to see the U-turn taking place in 1979. But it really shines light into something called the Jevons paradox, which is basically coming from a British economist from the 1800s who looked into the coal market, coal industry in the UK back in the 1800s. And I think he was 29 years old when it happened. And he wrote a book. He basically looked at the way the coal usage goes along throughout the years in the UK. And he saw that the more efficient they became at using coal, the more coal they ended up using. And it became known as the Jevons paradox or the Jevons theorem, which basically has other facets, has other analogous examples in real life, such as, say I get a promotion tomorrow and I get more, my salary doubles. You can guarantee that in 1 month I'm going to have a new car. It's probably going to be a much better car than what I have now. Because the car that I have now, it just became cheaper for me to have the car I have now. My house will also become better. I'm no longer going to be in an apartment. I will probably get a house. And it goes on like this. you see that in Black Friday with the day after Thanksgiving with the sales. If you ask anybody, they will agree that any sane person will agree that they have spent more money than they would have otherwise spent, even though there was sales, you know? So yes, things became cheaper, but I spent more. There are some limits to it, to the Jevons paradox, like for instance, you cannot really drive more than 15,000 miles a year. I mean, it's not like, even if the gas becomes cheaper, you're not gonna drive crazily. There is so much you can do, but I mean, it's a powerful principle.
Does the
Yeah.
global data here include the United States data, or is that without United States?
Sorry, which one? What is the question?
I'm asking if the global data includes the United States data, or is that without the
Yes, it
United?
includes the United States data. One weakness of this plot is that it does not take account of population growth. So the CO2 emissions is not per capita. So energy consumption is per capita, but the energy emissions, the CO2 emissions is not. So that's one of the weaknesses of this plot. Maybe in the next paper I will try to see normalize it maybe. Because population also increased over the years. Now, for our stuff, we see US crude oil production by state. We have Texas, 2 million barrels per day, roughly. New Mexico, 0.7, North Dakota third. 2 years ago, North Dakota was second, I believe. Then Colorado is fourth, and then Wyoming. And a lot of that is down to sort of artificial reasons, in a sense of California is not there. I can guarantee you that California would have been easily second if some unfavorable for oil and gas exploration and production legislature wasn't there. Colorado is a little bit of a strange case due to the fact that Colorado for years was what they call a purple state. So it was like alternating between what it's voting in general over the years. There is a lot of areas in Colorado that they have, the legislature is structured such that it's a little bit like the federal government in the US with the states. Sometimes the federal can overrule the states, sometimes the states can overrule the federal. It's the same thing a little bit of what happens in Colorado with counties and cities, but in general, it's a little bit tough to get anything about fossil fuels going on now in Colorado. I mean, I gave a research seminar in Colorado School of Mines last spring break. And I remember talking to one of the professors there, and he said that going to the state and asking for money for a fossil fuels project is almost like swearing at them, you know? It's like they get defensive, like something you are completely illogical or something. So yeah, Colorado could have been producing much more in general. Wyoming is around where it could be. North Dakota has had some great years in the early 2010s. Yeah, I mean, things are dynamic. Texas has a lot, so it will be first for a long time. I don't see anything changing. Now, for natural gas, it's a little bit of a different story. Also, notice that it's dry gas. So, okay, if it was natural gas, there is a question about the natural gas liquids. Where do they go? Do they go to the oil? Do they go to the gas rankings, let's say? But you have Texas first. You have Pennsylvania second. You have Oklahoma third, Louisiana, West Virginia. But what is interesting here is that the amount of shale that plays a role into this. I think, okay, Texas, you have Barnett, you have Eagle Ford, you have the Permian Basin, blah, blah, blah. Pennsylvania, you have Marcellus. Oklahoma, you have Fayetteville, some others. Louisiana, you have the Tuscaloosa shale, you have some others. In West Virginia, you have Utica, part of Marcellus as well. I don't know to what extent it's being explored there, but yeah. And I think you need to get down to California. I don't know what the ranking is right now, and Alaska to get to purely conventional sort of production. And even then, there is the Monterey Shale in California and some others that are very, very potentially prolific, you know. But yeah, I think they were saying that for me when I was a student, but certainly for you guys, you will definitely work with shale at some point in your careers. If some of you are already working on those stuff. And here is some, let's see. This is not inclusive. It doesn't have everything, but you see some, you see the backend, very important for us, extends to Canada. You see the Eagle Ford in Texas extending down to Mexico. You have the Tuscaloosa across Louisiana, all the way to Mississippi. You have the Haynesville in Louisiana. You have the Woodford all the way to Oklahoma, Fayetteville in Arkansas. Let's see, you have the Monterey in California. You have the Niobrara in north Colorado, east of Aurora. You have a lot of, yeah, the Utica, obviously, the Marcellus, and so on and so forth. Oh, yeah, the Marcellus, the Utica, in the Pennsylvania region, West Virginia, kind of. New Albany Shale, and so on. Of course, the shales are not the same. Shale to shale are very different. Nevertheless, yeah, there is a lot of opportunity there, and we will see in the next class, next in well completions with advanced stimulation techniques, how important how shale became so important, like technology-wise, even from this class, because to learn hydraulic fracturing and completions, we need to have a good understanding of geomechanics. How does the rock behave? So this class is basically, if I can put the whole class in one sentence, we're basically gonna learn how the rock behaves under stress. So we're gonna try to develop sets of equations, relationships about how does rock and stress interact. Like how does the rock deforms when it's under stress? Now, deformation is a little bit of a qualitative term. In mechanics, we really use displacement for deformation. And even better, we use the dimensionless version of displacement. Does anybody know what that is? Yeah, I think you said it. Yeah, but what is it in mechanics? Yeah, no. Yeah. Strain. So we are gonna relate strain with stress. Yeah, you stress the rock a certain way, you get this deformation. You can quantify it in terms of strain. Similarly, you deform the rock, you get stress. And in the same way that if you take a numerical simulations class, numerical reservoir simulation, you learn how to relate pressure and saturation, right? So you are learning about fluid flow through those rocks. In this class, we are gonna learn about stress strain behavior, stress deformation behavior. And there are many people nowadays, they have two simulators. They have one for stress and deformation and one for fluid flow. And they try to combine the two, have them run at the same time because one affects the other. In this class, we are more interested on the, exactly. And our first module will be on the subsurface stresses, and which are basically acting as basically the stresses that if I have this rock down the subsurface, I have some stresses acting on it from the earth, just because the material is placed underground. And we're going to talk about those. There is a lot of that we can talk about in regard to that. In the second module, we will develop constitutive models. So what I described earlier, like stress deformation behavior, how does stress relates to deformation? Or more quantitatively, how does stress in units of dimensions of pressure, because it's stress divided by the area it's applied to, impacts the strain behavior. It's a constitutive model that describes that. And the easiest one, which we are going to base a lot of stuff, and a lot of stuff are based on, is linear elasticity, which is what you are measuring in, what you are learning in your solid mechanics class. Is basically taking Hooke's law and applying it in 3 dimensions. And of course, building on that. And it's module 2 is the most mathematical one. The one that the students really don't like, but it's like something that we have to go through. I think graduate students like that more than the undergrads because they see more application. Undergraduates like more applied stuff. And I understand that I was undergrad too, I was a graduate too, and I also had a tough time in those classes. Module 3 is gonna be rock failure mechanism. We are gonna see in what ways can rock fail and how can we model that. We are gonna talk about tensile failure, which is very important because, for instance, hydraulic fractures that we do during fracking are tensile failures. Earthquakes that take place are basically movement along faults is shear failure, shear compressive failure. You also have shear collapse failure that is possible. We're going to talk a lot about those. They have every failure mode has its own criterion, etc., etc. Module 4 is wellbore stability. And this year I plan on incorporating some wellbore integrity in it. But basically we see, okay, we are drilling a well. How do we make sure that it's stable? And what kind of failures do I need to worry about when I'm drilling a well, when I have a well? So now not only I have a well, I have a piece of earth that I'm modeling, I also have a well inside that impacts the stress field around it. So if I want to model the stress field around a well, I need to take account of its, how does its presence, because I removed a piece of rock and I filled it up with fluid. This created some disturbance in the area around it. And I mean, that's gonna be the 4 modules of this class that we are gonna start next Wednesday. And then we will be ready for the next class, which will be more applied, which will be more well completions. I mean, thank you everyone, the 2 people online and the 2 people in class that joined. And I will see you on Wednesday. And like I said, it's gonna be a shortened office hour period on Tuesday because of a faculty meeting. And yeah, I will send an announcement for that. Oh yeah, and by the way, now that I remember, you guys oh, there is a question in the chat. Alaska is around 400,000 barrels per day from there must be the that must be the Prudhoe Bay production. Yeah. If you go to Blackboard and you go to module 0, you will see the lecture 1. That's the recording of lecture 1. That video has the screen I was sharing plus the camera on the top right. And now, obviously, I mean, there is nothing here that you will be tested on. Nevertheless, also I was late in posting I forgot. I went to it and then I remember I didn't post the lecture. But you can have the lecture immediately after the processing ends by going to the Zoom meetings link, and then go to cloud recordings. You will see all the files here. And it's 3 files. One has just the screen I'm recording, one has just the camera, and one has both. I just took the one that has both and I put it on the module folder just to make it easy on you. It doesn't mean that this is the one you have to watch. Like I might have written accidentally behind the camera. So you might want to see the screen I'm sharing just for that. But generally, yeah, I mean, it's available. It's going to be available to you. I think it takes about 40 minutes for processing, 40 minutes to 1 hour after the lecture is over, as soon as I stop recording, and it should be ready. So, yeah. Thank you very much, and I will see all of you on Wednesday. Are there any questions before I go? Awesome.
Will,
Yes.
is there any reading? I looked for a schedule to try and stay ahead of the readings. Is there anything we should read before module 1 out of the textbook?
Not necessarily. I would say if you go to module 1 and you skim through the slides, if there is some areas that seem to not flow that well, you can go to the book and see the textbook and see the corresponding sort of sections. Maybe the book makes more sense. Or you can always find material online that is related to it. Otherwise, you can wait until we go through it in class and ask me then, or always, if you come to the office hours and you want to ask, or send me an email if the office hours are not convenient, and I can help you through that, or the TA, of course.
Thank you.
Thank you, sir. And thank you, Justin and Joseph, for joining the class, and Malek and Hakim. Oh, wait, there is another question, Joseph.
Yeah, hello, sir. Yeah, I just want to ask, if, for instance, maybe I missed to attend any class, and because of time, because of my nature of my job, because like now.
Yeah, the lectures are available, are going to be available, the recording.
Yeah,
It's
so there's
better,
no penalizing that.
Yeah, it's better if you attend in terms of you can ask questions right along as I go along. But I mean, if your job doesn't allow it, I mean, you can watch the lectures and then see if you have any questions. It's going to be a little bit harder, obviously, but I mean, it sounds like you don't have many options.
Yeah, no, I'll be attending, but at times, sometimes maybe it's not, I don't have that chance to join the class, so I can go back again to attend to listen to the recorded class. Yeah.
Yes, of course. And also, if the class is a little bit too complicated, you can also watch it again and go slowly, stop the video, start again. Yeah. Thank you very much. Have a nice rest of your day. Stop recording.